You're driving over a bridge. It was built just 40 years ago, but you see rust stains bleeding through the concrete, chunks are missing, cracks spiderweb across the surface, and you wonder, is this even safe? There's a dome in Rome, the Pantheon, with not a single steel bar reinforcing it. It has stood for nearly 2,000 years. Earthquakes, floods, the relentless march of time itself, not even a scratch. For more than 13 centuries after the Roman Empire fell, it was the largest dome of any kind in the world. It remains the world's largest unreinforced concrete dome. So here's the question that should keep engineers up at night. Why do our expensive modern projects start to crumble in just a few decades, while ancient Roman structures have remained pristine for millennia? What did the Romans know that we've forgotten? Section 1. Many people wonder why ancient structures seem to last forever, while the things we build today feel almost disposable. This is not just nostalgia. There is a fundamental difference between the concrete of the past and the concrete of today. The main issue is a fatal flaw we engineered into our own designs. We live in an age of concrete. It's the second most used substance on Earth, right after water. It's the literal foundation of our world, our homes, our skyscrapers, our highways. But we built this world on a material with a surprisingly short lifespan. Modern concrete is incredibly strong when you press down on it. That's what's called compressive strength. That's why it's great for pillars. But it's weak when you pull or bend it. It has poor tensile strength. The modern solution was supposed to be a brilliant innovation from the 19th century, reinforced concrete. The idea is simple. You take that vulnerable concrete and embed a skeleton of steel bars called rebar inside it. The concrete handles the crushing forces and the steel handles the pulling forces. Together they create a super material. And for a while it worked. But there was a huge problem. We had unknowingly hidden a self-destruct mechanism in the very heart of our creations. That fatal flaw is the steel itself. Here's why. Concrete looks solid, but it's actually porous, like a hard sponge. Over time, tiny cracks form. Water, oxygen and salt from winter roads seep through these cracks until they reach the steel. And when they do, a chemical process begins: rust. Let's get into the exact numbers of this problem, because they're terrifying. When the steel in rebar corrodes, the rust products occupy 5 to 10 times the volume of the original steel. Think about that for a second. For every cubic centimetre of steel that transforms into rust, you have up to 10 cubic centimetres of expansive material trying to escape. This rust exerts a pressure of 3 to 4 megapascals on the surrounding concrete. Concrete has excellent compressive strength, but its tensile strength, its ability to resist being pulled or stretched, is only about 10% of its compressive strength. So we have a perfect storm for disaster. A massive expansive force attacking exactly the weakest point of the material. It's like trying to contain an internal explosion. And once the first spiral happens, when the first chunk of concrete breaks loose, the process accelerates exponentially. The now exposed rebar corrodes faster. More rust creates more pressure. More pressure causes more spiraling. It's a feedback loop of destruction. Here's the most ironic part. We put the rebar there to strengthen the concrete, but without proper protection, it becomes the very mechanism of the structure's own destruction. This is called spalling. A tiny crack becomes a big one, chunks fall off, and the whole structure starts tearing itself apart from within. So we are left in this strange spot. We have a material that is designed to fail. We are locked in a ruinously expensive battle against the inevitable decay of the very thing we chose to build our world with. What if there was a better way? What if the answer wasn't in adding more steel, but in looking to the past? Section 2. The quest for an answer. To find the secret to immortal concrete, we must become detectives. We have to look back and study the clues left behind by the master builders of Rome. Our first stop is the Pantheon. That massive 142-foot dome has no steel rebar at all. By modern standards, it shouldn't be this durable. It defies the logic of our own material science. And it's not just the Pantheon. Travel to the coast of Italy, to the ancient harbour of Caesarea. Roman engineers built huge concrete piers directly into the violent sea. Modern concrete, in that environment, can fail in just a few decades. Yet parts of these Roman structures are still there, after 2,000 years submerged in salt water, Wait, stop for a second. Let that sink in. Concrete that's stronger after 2,000 years submerged in salt water. This defies everything we know about corrosion. How is that even possible? Here's where it gets fascinating. Research reveals the seawater didn't destroy the concrete. It actually made it stronger over time. When seawater penetrates Roman concrete, it dissolves the lime inside. But instead of destroying the structure, this initiates an extraordinary chemical reaction. The dissolved lime reacts with the volcanic ash in the mix, forming crystals of a rare mineral called aluminum tobermorite, or Al tobermorite. These crystals don't just fill gaps, they create an interlocking structure of microscopic plates that reinforces the material. Researchers from the University of Utah discovered that these crystals continue to grow for millennia. They fill pores, strengthen bonds, and create an increasingly resilient structure. It's as if the concrete has an immune system that actually gets stronger with each attack from the salt water. The more the sea pounds against it, the more these beneficial minerals form, the stronger it becomes. The concrete is literally building itself stronger with every passing century. Compare that to modern structures. Concrete exposed to seawater typically begins to deteriorate within 20 to 30 years. The salt accelerates rebar corrosion, and the structure enters progressive collapse. Roman concrete. It's thriving 2,000 years later, constructing itself more robust with each century. These structures all share a common ingredient: opus caementicium, Roman concrete. For a long time, the secret was thought to be a special volcanic ash called pozzolana. The Romans mixed this ash with lime to create a binder that was incredibly stable and water-resistant. This pozzolanic reaction was key, but it wasn't the whole story. It couldn't explain everything, especially a strange anomaly found in every sample of Roman concrete. Scattered throughout the material were millions of tiny, bright white chunks. For decades, scientists dismissed these lime clasts as a sign of sloppy mixing, a defect. But for some researchers, that explanation just didn't add up. Admir Masic, a materials scientist at MIT, posed a simple but profound question. If the Romans put so much effort into creating this remarkable material, why would they be so consistently careless? It made no sense. He decided to investigate these supposed flaws, not as a mistake, but as a clue. What if they were intentional? Section 3. The secret recipe reveal. Using advanced imaging, Masic and his team analyzed 2,000-year-old concrete from an archaeological site in Italy. They weren't just looking at the material. They were zooming down to the nanoscale to understand the exact chemistry of these little white chunks. What they found was transformative. The structure of the lime clast suggested they had been formed at extremely high temperatures. This went against everything we thought we knew. The standard theory was that Romans made concrete with slaked lime, lime that is pre-mixed with water into a safe paste. But the evidence pointed to a far more extreme process called hot mixing. The researchers realized the Romans were likely adding quicklime, a more volatile, unslaked form of calcium oxide, directly into the mix with the ash and rock, then adding the water. The chemical reaction would have happened inside the concrete itself, generating immense heat, temperatures reaching 200 to 250 degrees Celsius. This high-temperature process created chemical compounds that don't form in modern concrete, and it also left behind small, brittle pockets of unreacted, highly reactive lime. These pockets were the lime clasts. But here's the critical detail. The Romans understood perfectly. Not all volcanic ash is equal. The Romans transported specific ash from the region of Pozzuoli, near Naples, sometimes hundreds of kilometers away, to build structures all across the Mediterranean. Why? Because that specific volcanic ash had the exact chemical composition needed. The pozzolana from Pozzuoli is rich in aluminum silicates in a perfect proportion. When mixed with lime and water, it creates a chemical reaction that forms uniquely stable compounds. Roman writers like Pliny the Elder and Seneca extensively documented the special properties of this ash. This shows us something important. The Romans weren't just following a recipe. They deeply understood the properties of their materials. They tested, experimented, and refined their formulas over centuries. This empirical knowledge, based on careful observation, was as sophisticated as our modern materials science. The lime clasts weren't a mistake. They were a brilliantly engineered feature. They were a hidden reservoir of healing power, waiting patiently for the day they'd be needed. The Romans hadn't made a flawed material. They had made a smart material. They had invented self-healing concrete 2,000 years before we ever came up with the term. Section 4. An ancient immune system. So, what was the function of these brittle, little white chunks? This is where the true genius of the Romans reveals itself. The lime clasts are the heart of an automatic repair system. It's like the concrete has its own immune system. Here's how it works. Think of a Roman wall at a microscopic level. First, a tiny crack begins to form. It's the same kind of crack that signals the beginning of the end for our concrete. Water from rain seeps into this fissure. Next, the water finds one of the millions of lime clasts. The water dissolves the reactive clast, creating a calcium-rich solution that flows into and floods the crack. Finally, the real transformation happens. This solution recrystallizes into calcium carbonate, effectively stitching the crack shut. But it also reacts with the surrounding volcanic ash, forming new stable minerals that reinforce the repaired area. The crack isn't just plugged, it's healed. The wound becomes a scar as strong, or even stronger, than the original material. You might be thinking, this sounds too good to be true, and I thought the same thing. So researchers at MIT put it to the test. Here's exactly what they did. They made 2 batches of concrete, one modern, one using the Roman hot mixing recipe. They then cracked both samples and ran water over them. The results were incredible. The cracks in the modern concrete stayed open, but the cracks in the Roman-style concrete had completely healed themselves within 2 weeks. 2 weeks, autonomous healing. No human intervention required. This is the genius of the old masters' approach. Our philosophy is to make concrete resist damage. The Roman philosophy was to accept that damage is inevitable and build in a system to repair it. They didn't just build for strength, they built for resilience. And if you're finding this dive into lost ancient wisdom valuable, do me a quick favor and hit that like button. It genuinely helps get this knowledge to more people who need to see it. Thanks. Section 5. Our modern disposable world. Now that we understand the Roman secret, the flaw in our approach becomes painfully obvious. As we said, the problem is the steel rebar. We designed a system where the concrete's main job is to protect the steel from rust. But concrete is porous, and it's destined to fail at that job. Over time, carbon dioxide from the air seeps in and slowly neutralizes the concrete, breaking down the protective alkaline shield around the steel. Once water and salt reach the now unprotected rebar, rust begins, and the self-destruction feedback loop kicks in. When a crack forms in Roman concrete, it's an opportunity for healing. When a crack forms in our concrete, it's a death sentence. Our obsession with speed makes it worse. Modern concrete is designed to harden in just 28 days. This is great for project deadlines, but terrible for durability, as it creates more internal stresses and microcracks right from the start. Roman concrete cured much more slowly, developing its strength over a longer period, resulting in a more stable final product. Their philosophy was one of patience. Ours is one focused on the next fiscal quarter. We traded eternity for efficiency. Let's talk about the real cost of this systematic failure. And it's not just money, though that's astronomical. In the United States alone, we spend more than $125 billion per year just maintaining and repairing concrete infrastructure. That's more than the entire GDP of many countries. And that number is growing. The American Society of Civil Engineers estimates we need $4.5 trillion over the next 10 years just to bring our existing infrastructure to an acceptable state. Bridges are failing, parking garages are collapsing, coastal structures are disintegrating. But the environmental cost is even more devastating. As we mentioned, cement production creates 8% of global carbon dioxide emissions. But here's what that really means. If the cement industry were a country, it would be the world's 3rd largest emitter, behind only China and the United States. And because our structures last only decades instead of millennia, we're trapped in a vicious cycle. Demolish, rebuild, demolish again. Each cycle releases more carbon. Each cycle consumes more resources. Each cycle sinks us deeper into an environmental crisis. The Romans built once, and it lasted 2,000 years. We rebuild every 50 years. Do the math. That's 40 times more material, 40 times more energy, 40 times more emissions for the same functionality. Section 6. The future is ancient. For centuries, this knowledge was seen as a historical curiosity, but that is changing fast. Scientists are now in a race to reverse engineer this 2,000-year-old technology for the 21st century. Admira Masik's team has already started a company to commercialize Roman-inspired, self-healing concrete. The idea isn't to replace our modern materials entirely, but to enhance them with this ancient wisdom. Imagine building bridges, tunnels, or buildings that have a design life of centuries, not decades. Infrastructure that requires dramatically less repair. The economic savings would be in the billions. Then there's the environmental impact. Cement production accounts for a staggering 8% of global carbon dioxide emissions. This Roman-inspired process is less energy-intensive because it requires lower temperatures than modern Portland cement production, about 2/3 of the heat needed for traditional cement. More importantly, if our structures last 10 times longer, we'd need to produce far less cement for replacements. This could be one of the biggest steps we take toward making construction sustainable. But the innovation doesn't stop with the Roman recipe. The race to reinvent concrete is happening right now, and some solutions are surprisingly creative. Scientists have developed concrete with living bacteria. Yes, you heard that right. They incorporate dormant bacterial spores, usually Bacillus species, directly into the concrete during mixing. When a crack forms and water enters, the spores wake up. The bacteria begin feeding on calcium lactate, which is also mixed into the concrete, and produce limestone as a byproduct. This limestone fills the crack from the inside out, healing the damage autonomously. Other companies are using a different approach. Special aggregates filled with healing agents that are released only when the concrete cracks. Researchers at the University of Southern California created hollow particles that burst under stress, releasing materials that chemically react to seal the fissure. And there's even concrete that uses conductive carbon fibers to detect damage through changes in electrical resistance, essentially giving concrete a nervous system that can alert engineers to problems before they become catastrophic. The challenge: cost. Bacterial concrete can cost 3 to 5 times more than traditional concrete initially, but when you consider it could last 100 to 200 years instead of 50, and factor in maintenance savings and reduced environmental impact, the calculation changes dramatically. Of course, there are challenges to widespread adoption. The specific volcanic ash the Romans used isn't available everywhere. Researchers are now working on creating synthetic versions or using industrial byproducts, like fly ash from coal plants, to mimic it. There's also the inertia of the construction industry, which is built around speed and upfront costs rather than life cycle thinking. But the movement has begun. So there you have it. The secret to concrete that lasts is not some unobtainable magic. Roman concrete was smarter. It was alive with a potential for healing that we traded away for short-term strength and construction speed. They embedded resilience into their material, while we embedded a fatal flaw. For centuries, we wondered how they built things that lasted. Now, we finally know. And with that knowledge, we have the chance to do more than just admire them. We have a chance to learn from them. By combining ancient wisdom with modern science, we are on the verge of building a future that is truly meant to last. The choice is ours. Continue down the path of disposable infrastructure that crumbles in decades and poisons our planet with emissions, or learn from the masters who built for eternity. If you found this journey into the past useful, and if you're tired of the modern disposable way of building, do us a favor and hit that subscribe button. We're diving deep into more lost technologies that could change how we live. And let me know in the comments, what other ancient techniques do you think we should be investigating? So there you have it. We've been building our entire modern world on infrastructure designed to fail. Every bridge you cross, every building you enter, every parking garage you park in is slowly self-destructing from the inside out, and we just accepted this as normal. Think about that for a second. We normalized planned obsolescence, not just for our phones and appliances, but for the very foundation of our civilization. The Romans built the Pantheon once. 2,000 years later, it still stands. We've rebuilt most of our bridges and highways multiple times in just the last 50 years. Imagine the trillions of dollars we'd have saved if we'd just built them right the first time. Imagine the billions of tons of carbon dioxide never released. Imagine the millions of hours sitting in traffic while crews patch crumbling infrastructure that wouldn't need patching. But here's the thing. Concrete isn't the only material where we completely lost the plot. Medieval blacksmiths knew how to make iron that never rusted. Medieval carpenters built with wood that lasted centuries, not years. They understood something fundamental about durability that we've forgotten. The difference? They built things once, properly. We build things fast, cheaply, and then rebuild them over and over and over again. We traded permanence for profit margins. We traded craftsmanship for quarterly earnings. And the craziest part? The knowledge to fix this isn't lost. It's just ignored. Companies that could revolutionize construction with self-healing concrete exist right now. The bacterial concrete, the Roman hot mixing technique, the sustainable alternatives, they're all proven. They work. But the industry moves slow because the current broken system is profitable for someone. So what do? We learn. We share this knowledge. We demand better. If you found this valuable and you're tired of living in a disposable world, hit that subscribe button. We're exposing more of these lost technologies that could actually change things. And listen, if this blew your mind, you need to see what we found about iron and wood. Medieval iron that never rusted versus modern iron that crumbles in months. Wood that lasted 800 years versus wood that rots in a decade. These aren't just cool historical facts. These are techniques some people are using today to make things that actually last. I'm putting both videos on your screen right now. Watch whichever one grabs you first, but you're going to want to see both. Drop a comment and tell me what other medieval technology should we investigate next. Thanks for watching.